independent samples t-tests, surely you knew that there was going to be a dependent samples t-test, and that's what we're going to get into today, so let's get into it. We are going to look at dependent samples. We're going to look at a full example. We're going to look at confidence intervals for dependent samples, the relationship between standard error and sample sizes again, and we'll look at some dependent samples t-tests in R. Dependent samples t-tests. With dependent samples t-tests, we are interested in comparing two means like we have been doing all along, nothing new there. But now these two means depend on each other and relate to each other in some way. They're matched pairs of data and might have come from, for example, a before and after treatment measurements. In independent samples, we take the average of both groups and take the difference between them and compare it to the null, usually that there is zero difference between the groups. In dependent samples t-tests, we compute the difference of before and after treatment, then take the average of those differences and compare it to... What do you think the null hypothesis is going to be for our dependent samples t-test? Make a guess. Just like in independent samples t-test, we are going to compare to the null hypothesis assumption that there is no difference between before and after treatment. We always start with the assumption that there is no difference, no treatment effect, and no change. So let's say you're on a diet for a few months. We're going to assume that your weight does not change from the first time that you weigh yourself to the last time that you weigh yourself. Now our subscript is going to be D for differences. So we have mu sub D here equals 0. So that is the average amount of difference equals 0 or does not equal 0 for a two-sided. We also have a one-sided where we can say that mu is going to be less than 0 or that mu is going to be greater than 0. We can also write it out as the post-score minus the pre-score equals 0 or the pre-score minus the post-score equals 0. It's whatever's more convenient depending on the example, just make sure you keep it consistent. So let's say that we have 10 students from this statistical literacy class. I measure your statistical literacy knowledge at the beginning of the semester, then at the end. So first off, what is the null hypothesis? Second, what are my degrees of freedom? Third, what mean am I going to compare against the null? And fourth, what is my standard error? Let's investigate. Firstly, the null hypothesis. The null hypothesis here is that there is no difference between your scores after a semester of statistical literacy and your score at the beginning of statistical literacy, that the difference is going to be 0 in your statistical knowledge. What are my degrees of freedom? Well, I had 10 of you. And instead of in independent samples where we have one group and another group and we have to subtract 1 degree of freedom from each group, now we have technically one group, but it's measured twice. You might be able to consider it 2 groups, but it is the same people. So now we only have n-1 degrees of freedom. It's like a one sample t-test again. So here we would do n-1, 10-1 equals 9. Remember that the n is the number of subjects, not the number of observations. So again, if I took a pre and a post-test score for 10 people, I would technically have 20 observations, but there's only 10 people involved in the study. And what mean am I going to compare against the null? The average of the difference scores, which we will see how to calculate in just a second here. And my standard error is just going to be the standard deviation of the differences divided by the square root of n. Here's our sampling distribution of differences in the means. It's our same curve as usual, but now instead of doing just one sample mean or the difference between means with independent samples, we are now looking at the differences between dependent means. And now we have our subscript mu sub d. Here is the statistic for our dependent samples t-test. It looks just like all the rest of our t-tests really when we have the calculated sample mean, which is the difference between pre and post-test scores. Then we have the hypothesized difference, and then we have the standard error. Here's our equation again, where we take our samples, we get the average of the post-test scores minus the average of the pre-test scores, and we get an average difference, and we can write it as just x bar sub d. Then we have our null, where we would have a suspected null idea, the post scores minus the pre-scores, and we divide by our standard error as always. So what is our null hypothesis for dependent samples t-tests? Much like our independent samples, we're going to assume that there was no difference from before and after treatment. And just like our independent samples, where we had this term here, it's actually just 0. So we can drop that part out and we are left with just this part of the equation. Now I ask this every time. If the null were true, would you expect that every sample of pre-scores minus post-scores be exactly equal to 0? Why or why not? As you already know, samples can be a bit fickle, and because of random error and chance, the differences will not always be exactly zero, even if the null hypothesis is true. Just like before, we want to find this range of zero enough. And if our test statistic falls outside of that zero enough range, either really low or really high, we can reject the null hypothesis and conclude there is a difference in pre- and post-test scores. Let's go through an example. I'm going to walk through the entire process of doing a dependent samples t-test by hand, but again, I'm not going to make you calculate all of this because it would take you a very long time and it's very error-prone. But let's still look at how we get where we're trying to get. Proponents of the Atkins diet, this is an old example from some book. I need to change that more to like keto diet or paleo. They claim that after 6 months of no carbs, dieters will have a substantial change in their weight. A random sample of 8 dieters showed the following weights before and after completing the diet regimen. At the 0.01 level of significance, test whether the Atkins diet had an effect on weight. So, what's the first thing we should do? State the hypotheses! And this one's fairly easy. The difference is equal to 0 for our null, and the difference is not equal to 0 for our alternative. Basically saying that the true average weight change after 6 months of a no-carb Atkins diet is and is not 0, respectively. This is a two-tailed test because we are asking about weight change. You could either gain or you could lose. There is no assertion of direction. Step 2 and 3. State the significance level and pick your test. We already know we're testing at 0.01, and we are doing a dependent samples t-test because that's the lesson for the day. Step 4, find those critical values. So if we go and look at our table, degrees of freedom, we had 8 people, so 8 minus 1, because remember dependent samples is n minus 1, not n minus 2. We have 7 degrees of freedom. If you go and look that up, we find a positive and negative critical value of 3.499. Why is it so big? Well, because we have very few degrees of freedom and because we are testing at 0.01, which is very strict. So that value is being pushed out further to the tails and it's going to be harder to find significance. If our test statistic is further out than 3.499 or more than 10.85 pounds of difference, then we can be confident that the true difference between the pre- and post-test measurements is not equal to 0. So here is, of course, the lovely curve. I have my null living up in here, and we are going to set that equal to 0. Then we have our critical cutoff values. We have 3.499 positive minus 3.499. And I once again translated this into the original scale. So if there is a difference from pre- and post-test scores, an average difference of more than 10.85 pounds or less than 10.85 pounds, we are going to reject that null hypothesis. Step 5, compute the test statistic. 207 to 228, lost 21 pounds. And so on. This person gained 6, lost 5, lost 15, lost 14, lost 14, lost 7. So on average, people lose about 8.9 pounds. Now, is that going to be significant based on what we already know from those visualized cutoffs? So here were all those differences that we already calculated. So again, some people lost as much as 21 pounds, one person gained 6 pounds. Now we want to do what we always do to get the variance and standard deviation. Think all the way back to months ago, where we subtract the average from all the differences, and then remember we have to square them all, because if we just added them all, they would add up to 0. So we square all the differences, then we take the sum of those squared deviations, we add them all up, and we get our sum of squares. If we add up all those sum of squares, we end up with 538.88. And if we divide by, we have to divide by n minus 1 because we're calculating variance for a sample, not the population. We end up with a variance of 76.98. But remember, that is still in the squared realm, and we want it to be in the original scale. So all we have to do is square root it, and our standard deviation is 8.77. So the participants on average differ from the average amount of weight loss by 8.77 pounds. I know, this looks pretty ugly. Don't look at it, don't look at it. It's how to calculate the standard deviation in one long equation. So let's just take the number and put it into our equation. Here is our lovely t-test, the same old structure as usual. We're going to put our average here, which we calculate the average amount of weight loss was 8.9 pounds. Our null hypothesis is that there was 0 difference, so we just subtract 0, which cancels out. Then we have 8.77, our standard deviation, divided by the square root of n. This whole thing is our standard error, which is equal to 3.1, We evaluate that statement and we end up with negative 2.87. Our t-statistic is 2.87. Where is that going to fall on our curve and what is going to be our decision? Bam! So what is our decision? Is it in the realm of 0 enough? Yes, indeed it is. In this case, we failed to reject that the true difference between the samples is not equal to 0, meaning that it might be. The true amount of difference might just be 0. So let's draw our final conclusions. We failed to reject that null hypothesis. There is not enough evidence to reject the null hypothesis that the true mean difference in weight is equal to 0, meaning that we cannot conclude that there was an effect. Although we did see weight loss for most of the participants, we might have not found significant test results due to inadequate power, due to small sample size. There's so few people. There's kind of a high amount of variation, especially because we had such a small sample. The standard deviation and the standard error are both kind of large. And we had a very strict alpha level of 0.01. So that could be part of the reason we did not find significance. Now let's make a confidence interval. Why not? For dependent samples now this time. Everything over here is going to be exactly the same. The only thing that keeps on changing is whatever we put for the point estimate. So for a one sample, we just put in our one sample. For independent samples, we put in the difference between the two samples. And now for dependent, we put in the average amount of difference between our two pre and post scores. Here is a confidence interval for the example we just did with the Atkins diet. We had 3.1 is our standard error. 3.499 is our critical value. Again, it's really high because we had a really strict alpha of 0.01 and because we had a small sample size. This is, of course, all of our margin of error. Our point estimate was negative 8.9. On average, people lost about 8.9 pounds. And if we actually calculate all this, we end up with this, our 99% confidence interval of negative 19.75 to 1.95. Did you notice anything about the confidence interval? So we can interpret this as we are 99% confident that on average people will lose as much as 19.75 pounds or gain as much as 1.95 pounds on this particular diet. Notice how our confidence interval contains that 0. If a confidence interval contains 0, it is not significant. This is because 0 is the actual expected mean difference under the null hypothesis. So this sample is not distinguishable from the null population. Thus, we fail to reject. Let's look at the relationship between standard error and sample size again. What would happen to the standard error, the t-statistic, and the critical value if we increase the sample size? Let's pretend that the variation and the mean are all the same for this example. So pause me for just a second and think, what would go up and what would go down if we increase sample size? Here's the example that we just did. Nothing is different yet. We have our sample size of 8, our standard error of 3.1, and our critical t of negative 2.86. But now let's see what happens if we were to increase our sample size to 16. So now here's the same example, but with a sample size of 16. First off, our standard error got smaller. Now it's only 2.19. Our t-statistic got larger. Now it's negative 4.06. And what's the other thing that's going to change? Our degrees of freedom, which changes our t-critical. Our t-critical went down to a negative and positive 2.947 when before it was 3.499. So to wrap everything up, if we were to increase sample size, all else being equal, we would get more degrees of freedom, which would lower our critical value. Basically, our critical values would move from the outside of the curve inward, making it easier to find significance. We would decrease our standard error because the larger sample size eats up some of that variance and we get a smaller standard error. And that smaller standard error is going to result in a bigger test statistic because it does not have as big of an appetite and can't eat up as much of this, so it'll result in a larger t-statistic. Let's try another example. Journaling is suspected to be positively associated with well-being, an increase in well-being. To test this, I give out a well-being scale to a group of 16 subjects at the start of the study. After 1 month of journaling, the well-being scale is re-administered. The average difference in well-being was 5.8 points, with a standard deviation of 1.2. At the 0.05 level of significance, test whether journaling increases well-being. This is bias on my part because I am an avid journaler and I think everyone should journal. Journal, it's very good for you and healthy. As always, step 1, state the hypotheses. In this case, there is some suggestion of direction. We're saying that there is going to be an increase in well-being. So our alternative is that the average amount of difference is greater than 0, and the null would be that it is less than or equal to 0. Step 2 and 3, we have our level of significance, testing at 0.05, and we are doing a dependent samples t-test. Step 4, get those critical values. We have 16 participants, so we have 15 degrees of freedom, testing at 0.05. You look that up on the table, you get positive 1.753. How do you know it's positive? Because you drew the picture, right? You are supposed to be drawing that picture. So if we were to visualize this, we can see that right here is a right side test. We have our positive 1.753. We are looking for a mean difference greater than 2.10, which we've already seen. It's going to be significant. I made it significant because I'm a big journaler. So if our test statistic is greater than 1.753 or more than 2.1 points of difference in that well-beingness scale, we can be confident that the true difference between the samples is not equal to 0. Substituting our sample statistics in the formula below, 5.8 minus 0 divided by standard error, 1.2 divided by square root of 16. I should be an auctioneer. We end up with 19.33. That is huge. We don't even have to look at the critical cutoff. So is our test statistic greater than 1.753? Yes, it's probably actually way out here somewhere. So it is super significant. Step 6, draw some conclusions. I've also, of course, created our 95% confidence interval right here. So using that or using our critical t-value and our test statistic, we will still come to the same conclusion that we reject the null hypothesis. The true difference in pre and post well-beingness scores after a month of journaling is not equal to 0. And we can say something like journaling for 1 month appears to increase well-being on average somewhere between 5.27 points to 6.33 points. Confidence interval. All t-tests, ... Though our last few t-tests look a little different, the essence of them is all the same. We take some sort of difference of means and we divide by the variation standard error of the group or groups. So there was our one sample, our independent sample, our dependent sample. And it's always, again, difference between means and dividing by some sort of standard error. Now, how do you know which one to use? Here's a little flow chart I have created. So you could ask, how many samples are there? Did you just take one sample? Are you comparing it to a known mean? You would use a one-sample t-test. If you know the variance, you would use that z-test, but if you don't know variance, you use a t-test. Here are the different hypotheses you can have. Were there two samples? Yes, okay. Were they repeated measure samples, meaning that you just asked the same person twice later on? Or are they completely independent? If it's independent, you do independent samples. Repeated measures, you do a dependent samples. So all t-tests are hypothesis tests. They compare some sort of average score to some sort of hypothesized, that null hypothesis average score. They have an unknown sigma, so we have to estimate standard deviation. And we use standard error with the associated degrees of freedom, whether it's n-1 for a one sample or repeated measures dependent sample, or n-2 for independent samples. Now that you have the 3 different types of t-tests in your toolkit, go through each one of these examples and see if you can figure out what kind of test it is, whether it's one or two-tailed, and if it's one-tailed, which tail is it? Pause me and try. Try it. Number 1, I want to compare the average score of one of my stats literacy courses to the average of my other stats literacy course. I have 2 independent groups, so that means I'm going to be doing an independent samples t-test, and it is two-tailed because I make no assertion of which class is going to do better. Number 2, I want to compare a sample of UT students' average hour of sleep to the national average with an unknown sigma. We are going to be using a one sample test because we only took a sample of the UT students, and it is two-tailed because, again, we make no assertion of direction. I want to know if the Fremont School District is performing lower than the state average on the STAR test. That lower gives us the clue that it is a one-tailed, and it's going to be a left tail because that's the less than. And it's a one sample because we are only comparing the one school district. I want to know which drug is better at reducing flu symptoms. I create 2 groups. One receives drug A, one receives drug B. What are we doing here? We have 2 independent groups, and it's two-tailed because there is no assertion of which drug is going to be better. And lastly, I want to know if allowing people to fidget to their heart's content changes their average math score. I first tell the students that they are not allowed to fidget for 1 week. Then the following week, I allow them to fidget all they want. I then compare the 2 averages. What are we doing here? We have this time a dependent sample because it's the same group and they were in both conditions. The first condition where they are not allowed to fidget, then they are allowed to fidget, and we check the difference between their 2 scores. And it's a two-tailed because there's no assertion if it increases or decreases that math grade. We've been dealing with 1 or 2 samples thus far, but what happens if we want to compare more than 2 groups? What if we have 3, 4, 5, 6, 7, 8, 9? Who knows how many groups? Can we just do a bunch of t-tests? Instead, we need an ANOVA. I will see you there. Dependent samples in R. This is how you would do a dependent samples t-test in R using summary statistics. So we would take that average from our weight loss example of negative 8.9. We have our standard deviation, the sample size, and our degrees of freedom. Then we ask R, again, using that QT function to get the critical values that we need, and we have that negative and positive 3.499. Then we just put all of our information into our equation where we take that mean difference, which is that negative 8.9, and we divide by the standard error, which is the standard deviation divided by the square root of n, and we get that same value that we got before, and we fail to reject. So here is how we would do that same example in R, but using the data rather than the summary statistics. Here is the pre-diet data, and here is the post-diet data. We take both of those and we're going to put them into our t-test. We have our post and our pre-data here. We're going to tell R that it's a paired test by saying paired equals t, which means true. And we're going to tell it that the confidence level is 0.99 rather than the default, which is 0.95. If you run that, you get the same results that we had when we did it the long way. Let's do another example in R again using data, but this time I'm going to use a bigger data set. Because when we're having to do things by hand, I have to do limited, smaller examples because it would be very tedious and take a long time to do all that by hand. So let's do a slightly longer one here. We'll use a bigger diet data set to determine if there is a statistically significant difference in the weight of participants before and after a 6-week diet. So here are our hypotheses. We have pre versus post-diet weights are not going to differ. The difference between them will be equal to 0. And the alternative, of course, is that they are not equal to 0. We can first look at some descriptive statistics. So the data I have here, it's in Canvas if you want to download it. I have diet data and I use this little $sign and I'm going to look at the column called pre-weight. And I can just ask R to take the mean. So I get 159 and the standard deviation was 17. And now I can look at the mean for the post-diet scores. So I would do again diet, $sign, weight 6 weeks. That is the column that has the post-weight scores. And I ask for the mean, I see 150. So it looks like there's about 9 pounds of difference, but we still don't know if it's statistically significant. So let's go and check. So here is the output from our example. We have 75 degrees of freedom. So how many people were in the study? 76, because with dependent samples, we do n-1 for our degrees of freedom. We have a t-value here of 13.962. Without even looking at a t-table or at the p-value, that looks very significant. And we can confirm this by looking at the p-value, which is 0.000000. So our p-value is certainly less than that 0.05 that we set our level of significance at. The confidence interval confirms this too. Here's our confidence interval, 7.49 to 9.96. And we do not contain 0 in that interval, so once again, we have more confirmation that this is statistically significant. We can conclude that the pre and post-diet weights are not the same. There is a statistically significant difference in weight before and after the diet. This is how we would write it in APA. We would have T75 equals 13.96, P equal to 0.00. And this is the full code, so this is how you would read in the data, how you can get the mean standard deviation if you really felt so inclined, and this is how you would get the t-test, where you put in the diet pre, the diet post. We tell R that it is paired, and we don't have to say anything about our confidence level because 0.95 is the default, but you can still write it, it doesn't hurt. So that's how you do it in R. I recommend you go and give it a try. See what you think. Go have fun. See you in the next one.